Welcome to our latest episode of HSC Chemistry. Today we're going to be talking about solids and liquids. Um, this lesson will be more based on vocabulary than theory, although we will be working through a few example problems. So first, about the structure of the atom. While we're talking about forms of matter, we should probably start by acknowledging, just starting on the same foot, starting on the same page, acknowledging matter. And matter is composed of atoms, according to atomic theory. Um, so in order to analyze the properties of these atoms, we will have to look at the components of these atoms. An atom is essentially mostly empty space. We have a nucleus made of protons and neutrons being neutrally charged, and protons being positively charged, so the nucleus is overall positive. And then that nucleus is orbited by negatively charged electrons. Um, and the properties made of these protons and neutrons and electrons, let's talk about them, right? First, let's talk about the atomic mass and the period numbers of these atoms. These depend more heavily on the nucleus. Each proton and each neutron roughly weigh around the same number of the same number of AMU, atomic mass units. Um, and generally, these will be the ones making up the mass, right? Um, the protons will be contributing the positive charge, obviously, and the electrons will be contributing the negative charge. And so we have sort of a balance of positive and negative. So usually a stable atom, or its most common form, is going to be neutral. We will go into isotopes a bit later, but that's not for this video. But an isotope is when your neutron balance is out of whack, and so your mass is different. There are also ions, which we will be discussing in this video, wherein electrons will be lost. And the reason electrons and not protons are lost is because protons are locked in with the strong force, locking in the neutrons. There is a weak force acting against this, but as its name implies, it's a bit of a weak force. But yeah, that's the atom. If you want to know more, please check out our other video on the history of the atom and how our atomic structures and pretty much our conception of it has changed. In fact, this isn't even the current model. The current model deals with an entirely new concept of orbitals that we unfortunately will not be able to get to in this video because it is a more basic video focused more around the Lewis model of the electron parts of the atom. But yeah, that's the structure of the atom for you. And of course, when talking about atoms, we must also talk about molecules, because molecules are the combination of a few different atoms. And these are combined with bonds, right? And with these bonds will be different. Really, the only ones that you will have to be comfortable with for now are the top two, ionic bonding and covalent bonding. And the difference between the two is that ionic bonding, as its name implies, is between ions. I discussed these a bit. Ions are atoms which either have too many electrons or too little electrons. And so what this allows the ions to do is to seek out ions that have the opposite of what they have. So, for example, you see chlorine over here, chlorine ions. Chloride, actually, as the ion name is, has a bit too many electrons, as denoted by the negative charge. And you can see sodium over here has a positive charge. The sodium ion has a positive charge, so it needs an electron. And so what happens, as you can see, is that they start giving electrons, right? So the sodium is given an electron by chlorine, and that's how the bond works. That's an ionic bond. Now, you see a different type of bond in covalent bonds where the electrons are shared, and that's because of the electrons in the outer shell. Really, the electrons in the outer shell dictate the specific bonds that you'll have. And this actually is a precursor to a bunch of their chemical properties, which we will be going over as we look at the periodic table later on in this video. But now let's look at the other types of bonds. We have metallic bonding, which happens generally in transition metals. Yeah, we won't be going over this in much detail right now, but you should know that it's ions of transition metals surrounded by free electrons, and that's how they bond. We also have a molecular bonding, which is pretty much a blanket term for a bunch of different intramolecular forces. And so the most common ones, as you can see here, are hydrogen bonds, which are pretty much small bonds, depending on the polarity of both molecules involved. Water, I'll give you a synopsis. Water is a polar molecule, which means that part of it is slightly positive and part of it is slightly negative. And because of this, the slightly negative parts are attracted to some of the slightly positive parts, and you have a very weak electrical attraction. This is actually really important in terms of chemical properties. We will be going over that later. Other molecular bonds include London's dispersion. Yeah, it's not vital to know a ton of these. So, now that we've talked about molecules and atoms, let's talk about elements and compounds. Over here, I was talking about the periodic table. And it's arranged in different groups and periods. Now, the groups generally, those groups are about the outer electrons. For example, the noble gases all the way at group 18 have a completely full outer shell. Well, if you look at the halogens at group 17, just need one more electron, and these are generally the most electronegative. In other words, they're the most electron hungry. And as you go back, group 1, the alkaline metals, the alkali metals, these are the ones that have the least amount of electrons generally. And so they'll want to give away their electrons more. So that makes them the least electronegative. That's enough about the groups. The periods. You can see that these are the rows, and these are sort of an indication of the mass. Now, the group also has to do with the mass, but that's just a general periodic trend that you'll have to read about later. The periodic table is especially useful because you can categorize these elements by virtue of their valence electron shells, as well as several other things. It just works together so nicely. Now, compounds. Compounds are where you have different elements attached to each other. For example, sodium chloride, NaCl. That's sodium and chlorine. And how you I want to make a very important distinction here. Molecules and compounds are not the same thing. Compounds are molecules, and molecules aren't always compounds. As you can see in this lovely visual, you can have molecules of elements, for example, diatomic oxygen, diatomic sulfur, and the list goes on. Whereas if you have molecules of compounds, those aren't going to be elements, right? Like, that's pretty obvious. Molecules are generally a superset for compounds, right? Because compounds are going to be a subset of molecules by virtue of their being a more specific type of molecule. So let's get to the topic, the real meat of this video. The title was Solids and Liquids. We're 9 minutes into this video and might as well treat you to the subject matter. Solids are going to be categorized in either crystalline or amorphous, and they're like this because they are locked in place, unlike the other forms of matter. They're completely squelched together. It's very difficult to move them and break these intermolecular bonds. Intramolecular. I should probably go over the difference between the two. Intermolecular means within a molecule. For example, these are the covalent and ionic bonds. Intramolecular, by contrast, is everything outside of the molecule, that the molecule as a cohesive unit does. And so a good example of these are the hydrogen bonds between different water molecules, whereas the covalent bonds that make up the water molecules which, by the way, have different types. There are polar covalent and there are non-polar covalent, but that's a video for another time. Yeah. So yeah, you have crystalline there, you have amorphous there. Simple, nice and simple. Now this is a physics class, and so, hey, did I say this was a chemistry class in the beginning? If I did, I'm so awfully sorry. This is a physics class. Sorry, I hope that was clickbait. This is a physics class, and we are also going to talk about density in the context of solids. Now, density, as you can see, denoted by this lovely Greek letter rho, is mass divided by volume. In other words, it's directly proportional to mass, it's inversely proportional to volume. And I am saying this out loud like this because it's important to know the correlation between stuff in an equation. It comes up a ton on like Science Bowl and USABO and USAFO and generally on tests. Teachers love asking about proportions because, well, to be fair, they do come up a ton in science. But that's density, which is essentially the amount of something in a given volume. Now, let's also talk about alloys for a second, because they have to do a bit with density. An alloy, so on the top left, you have pure metal. It's nice and pure, made up of a single molecule. And then you have these three different types of alloys. Now, you won't need to know these alloys in great depth, but what you do need to know is that by mixing a metal into a metal base, you can get usually a harder metal than you had before, right? Because if you add two metals, you're still going to end up with a metal. And so that metal is going to be harder because the molecules will make it less easy for the intramolecular forces of the metals to slide past each other, right? Like you can see, it's pretty easy for these molecules, these units in these pure metals to slide up and down, back and forth, and all sorts. But in a substitutional alloy, this is not the case because the molecules have been substituted, some of the molecules have been substituted for those of a different molecule, a different metal, as you will. And so because they're different sizes, different masses, well, generally different, it's harder for them to slip and slide past each other. Now, interstitial alloy sort of flips this by having small little metals, not enough to disrupt the structure of the pure metal, but enough so that they are stuck between the gaps, right? And they retain that quality of not being able to slide up or down. And finally, we have a substitutional / interstitial, which is just a combination of the two. Alloys generally make things harder, as you can see, because when things can't slip and slide past each other, they break a bit more difficultly. Now, the other half of this video is called liquids, solids and liquids. Now, on this slide, I'm sure you know what a liquid is, right? They have looser bonds than solids. These bonds are constantly forming and reforming as the liquid sloshes back and forth. And I want to make a distinction between liquids and fluids. Now, liquids, I just told you what liquids are, a specific form of matter. But fluids are a bit different because while all liquids are fluids, not all fluids are liquids, because a fluid is generally defined by a form of matter that is able to, well, take up the space of a container, right? And under this definition, gases are fluids as well, and some people will argue that plasmas and Bose-Einstein condensates and other forms of matter are liquids. Sorry, are fluids. Wow, I'm not on my game today. So those are fluids too. And so fluid and liquids aren't necessarily interchangeable, right? The main thing to take away is that gases are also fluids, and all liquids are fluids, right? And so now let's talk about pressure. You can have a pressure on a liquid. You can also have a pressure on a solid. In the same way, a liquid has a density because it is matter, and a solid has pressure. I just said that. Now, in dealing with pressure, there are just two equations that you're going to want to know the most. That's P equals F over A. In other words, pressure is directly proportional to force and inversely proportional to area. And you have P equals rho times G times H. Rho being density, as we just covered, G being the gravitational field strength on Earth. I want to contrast this with the gravitational constant. I'll give you a very quick lesson on this. Small g is going to be equal to 9.8 because that's a strength on Earth. Whereas big G, which is used in an entirely different equation dealing with the masses of the two objects divided by their radius squared, their orbit radius, that is. Big G is going to be a constant, right? It's called the gravitational constant for a reason. It stays constant everywhere in the universe, no matter where you are. If you're in the sun, big G is the same. And the reason that big G is able to do this is because I said before that it's inversely proportional to the masses of the objects. Now with G, we don't have to take that liberty with small g. Small g is going to be 9.8 approximately, and that's how we that's the amounts rather we multiply by our weight, our mass, to get our weight, right? Gravitational field strength is approximately 10 on Earth. And I don't want to go into another tangent, but I guess I have to, sort of. This isn't true everywhere on Earth, right? In fact, one could argue that it's only true on one specific point of Earth. Even if you assume Earth is a sphere, it's going, right? Because according to Newton's laws of relativity, gravity is more of an interference of space-time. I won't get into this, right? This is just basic physics, and so I would hate to get into relativity when I've planned a slideshow for solids and liquids. So where was I? Pressure equals rho, that's density, times G, that's the gravitational field strength on Earth, generally, times H, and H is the depth of the liquid, the depth of the fluid. I believe this equation can also be used for fluid, for gases. But importantly, it can't be used for solids, right? It just doesn't make sense to have depth to a solid, and yeah. So generally, it's used for liquids. Hopefully that's not misleading, because now we're going to be talking about buoyancy. Buoyancy is the force that opposes gravity when an object of rho density and m mass enters a fluid of rho density. As you can see in this visual, this helpful little visual, gravity is acting downwards on it, so buoyancy has to oppose it. Yeah, that's pretty much all you need to know. That's pretty much all the textbook says. I would like to add that there are equations that you might want to look up regarding buoyancy. Buoyancy and its relationship with pressure and viscosity have been pretty hotly debated. In fact, people haven't been able to find a proof for the Navier-Stokes equation, which relates viscosity with a bunch of different things, the Reynolds number, stuff you might want to look into. But essentially, buoyancy has to do with the relative density or relative mass, one of those values in relation to that of the object. And it's a comparison of the two. If the object has a lesser amount of that value, it gets to float. And you can actually determine what the percentage of the water margin is on that object, which is pretty cool. That's buoyancy. And our final concept is going to be surface tension. Remember when I was talking to you about, what was that? The polar objects? Sorry, the polar covalent bonds. Well, they have come back to haunt us. As you may recall, hydrogen bonds do happen between these polar covalent molecules. And water is indeed a polar covalent molecule, right? It's made up of covalent bonds, but it is a dipole, meaning that on one side is slightly charged, and the other side is slightly charged oppositely to that. And so what you have is that a surface, a molecule on the skin of the water, if you will, is pulled towards the center, right? There's no force that is pulling it upwards, whereas a molecule in the center, an inner molecule, as you will, is being pulled in all directions. And so that's where we get the idea that a water droplet looks more like a hamburger than an actual, like, physical description of a droplet, right? Like a droplet we usually think of as, a cone, an ice cream cone, an inverted ice cream cone. And so that's just not what a water droplet accurately is. Here's a general formula. That Greek letter, which I can't identify, I believe that's a lowercase lambda, but you'll have to check with the Greek experts for that. Surface tension equals 1/2 times the force divided by length, wherein force is directly proportional to surface tension and length is inversely proportional to surface tension. And again, I'm emphasizing this because tests really like to ask this. And so, returning back to our concept of surface tension, this happens in water because the surface molecule is pulled inwards, and generally the skin of a body of water is pulled inwards, and this really helps for organisms like the water strider and the basilisk lizard, who both need to be on water. And so the way they flit around on water is that their appendages, as you will, have very small hairs on them that distribute pressure evenly, that distribute the forces, the normal forces, evenly, and this allows them to efficiently stand on the water, right? Because with less force, with more surface tension, you have less force. With less force, you have less of a burden on the surface molecule being pulled inwards, and so you're able to skate on top of the water. Surface tension happens in pretty much all liquids, and I don't think the extent it has on gases is very large in magnitude. But yeah, that's about it. That's our lesson for solids and liquids. That's our physics lesson, I should say, on solids and liquids. And next week, we'll be covering a bit more about matter. We will get to gases soon, I promise. That being said, please watch the video on atomic history if you haven't already, because that's great backdrop to this, or supplemental material. And in general, yeah, thanks for watching. Goodbye.